So welcome to the next topic, which is polygon. So under the polygon, we'll be looking at the definition, some important polygon, number of diagonals, the number of non-intersecting triangles, the relationship between the interior and its corresponding exterior angle, some of the interior angles, some of the exterior angles, regular polygon, each interior angle of a regular polygon, the relationship between the central angle and exterior angle of a regular polygon, apodem of a polygon, radius of a polygon, and finally the area of a polygon. So that's our target. So let's start. So the first subhead is the definition. So a polygon is just a figure or a shape formed by intersecting three or more line segments such that at most two segments meet at a point, and also each segment meets other two segments. Because if you restrict it to the intersection of two segments only, so meaning that three lines can intersect, but it's not a polygon. So from the definition, see what I mean. So assuming from the definition, it must be three or more. So if you have this, so from the definition, this is a polygon. As you can see, it's a three-sided polygon. This is the segment 1, this is the segment 2, finally this is the segment 3. So you notice that each intersection here is only two segments, which is L1 and L1 and L3. Why this one is this L1 and L3? Why this is L2 and L3? Finally, this L1 and L2. So this is a polygon. It obeys the rule. It must be what? So a polygon is a shape formed by intersecting three or more line segments such that at most two segments meet at a point. The second, each segment meets an additional two segments. So as you can see, our first diagram is a polygon. At most two, and also each of them meets. So like line 1 now meets line 2 and 3. So but if you look at this, if you didn't specify at most the two segments meet at a point, you notice that someone can still, I decide to call this a polygon, but it's not a polygon, because here it has violated the first part, which is it must be two segments, not three. So this is not a polygon, but this is a polygon. So that's our polygon. This is not a polygon. So that's the first thing we need to know here. So the next subheading is some important polygon. But before then, someone might come up, I don't know. If you are talking about polygon, we always specify it must be specific, which is a convex polygon. So a polygon is either convex or concave. So we have convex. We have convex. We have non-convex or concave. So if you are everything we are going to do here will be based on convex polygon, because this is the actual polygon. A convex polygon is just a polygon that all the diagonals are inside the polygon. So I'm saying that this all the diagonals are in the interior of the polygon. The interior of the polygon. Why this? Not all the diagonals are in the interior. So some are outside the polygon. So see what I'm saying? For example, let me use a four-sided polygon. This is a four-sided polygon. You notice that this is the diagonal, is inside, is also inside. So this is a convex polygon. Well, look at this. This is a convex. This is a convex polygon. Well, look at this. So again, this obeys the rule of So this obeys the rule of the definition that two or more, that at most two segments meet at a point. So it's correct, but it's not a convex polygon. This is a concave polygon, because though this diagonal is inside the polygon, this is also inside. This is also inside. So this is diagonal 1, diagonal 2, finally diagonal 3. You notice that this one is outside. This is out. It's not inside. So this is a concave polygon. So actually what we are talking about is convex polygon. We don't normally pay attention to concave polygon. So everything we are doing here is based on convex. They are all convex polygon. So the next thing is to give some important, like give a table of important polygons. So next one, some important polygons. But before then, a polygon is named by the number of sides. So that's another thing you have to know. We name a polygon based on the number of sides. So I'll be preparing a table based on that. This is polygon, name of polygon. Name of polygon. Why is the number of sides? Number of sides. So that's our table. So the first one we know, the smallest So the first polygon we have here is triangle, so we have 3 sides. So the other one is 4, which is a quadrilateral, which is 4 sides. So the next one is a pentagon. Pentagon, that's 5. The next one is hexagon, that's 6. The next one is heptagon, that's 7 sides. The other one is octagon. Octagon, which is 8 sides. So we have nonagon, that's 9. So we have decagon, that's 10. So that's the special one. We're going to stop here. So let's go over to next subheading, which is the number of diagonals of a polygon. Okay. So we have the number of diagonals of a polygon. Number of diagonals. So that's the number of diagonals. Here, a diagonal is a segment joining two vertices of a polygon, non-adjacent vertices. So see what I'm saying? If you have a 4-sided polygon, so I'm looking at vertex 1 now, this is V1. This is a diagonal because V2 and V3 are adjacent to V1. Adjacent, this is the non-adjacent diagonal. Non-adjacent vertices, we get a diagonal. So from here, you notice that this is also non-adjacent to that. So we have 2 diagonals. Okay. Let's check. Triangle has none because the 3. This is V1, V2. So we have no diagonal. So the other one is, let's check 5. This is a 5-sided polygon. 3, 4, 5. So that's V1, V2, V3, V4, and finally V5. So I'm using V1 as the reference point. So you notice that this is non-adjacent to V1. This is also non-adjacent to it. So we have this 1, this 2. So this 3. This 7. This 4. Finally, this 6. That's 5. So we have 5 diagonals. So without wasting time, we notice something. Yeah, we have 3 triangles, we have a triangle, no diagonal. Quadrilateral, 2 diagonals. Pentagon, 5 diagonals. Let's get something here. We have what I'm saying. So generally, we have n times n minus 3 over 2 diagonal. So for any polygon, we have this V1, V2, V3. you notice that the number of vertices is also equal to v is always equal to n, because for if it's 3 sides, 3 vertices, 4 sides, 4 vertices. So these two are the adjacent. So this is the adjacent vertices. This is the adjacent. So we remove 2 out of the total sides or the total vertices plus itself. That's why we did this minus 3. Diagonal, you must join 2. So we need to divide by 2 because we don't count twice. If you notice, I did not count. I counted V1. I didn't count V3 to V1. I just counted V1 to V3. Why V2? V1 to V4. So we need to divide by 2. We don't count twice. So that's how the formula came about. So each of them, that's why we multiply by n. So each we have n minus 3 non-adjacent diagonals divided by 2. Finally, multiply by n to give the total. Each will have n minus 3 over 2. So the total is now times n. So that's a very nice formula. So whenever you're asked to find, if you can, let's test using it. Let's test the ones we've solved. So for pentagon, we have 5 minus 3 times 5 over 2, which is 5. So for quadrilateral, which is 4 minus 3 over 2, which is 2. So we are correct. Or triangle, which is 3 minus 3 over 2, which is 0. So the formula is very, very important in solving some questions. So the next subheading is the number of intersecting triangle. So this will also help us to get the sum of the interior angle. So you notice that for a pentagon, for a quadrilateral, a 4-sided polygon, we have 1 and 2 non-intersecting triangle. We don't join, so this is 2. So we have, if n is 4, number of triangle is 2. So what of pentagon? So we have 1. So we have 1, 2, 3. So if n is 5, number of triangle is 3. So let's take the last one before we get a general formula for that. So this is a hexagon. This is 1, that's 2, that's 3. So 1, 2, 3, and 4. So if n is 6, number of triangle is 4. So generally, we have, if you notice what is common, they go down by 2, 4 sides, 4 sides, 2 triangle, 5 sides, 3. So generally we have n minus 2 non-intersecting triangle in a polygon. In a polygon. So that's it. So let's go over to the next. The relationship between interior and exterior angle. Okay.